How to interpret wind tunnel data. Have you ever wondered how NASCAR teams make their cars so fast and stable on the track? A big part of that answer lies in wind tunnel testing. Today, we will break down how to interpret the data collected from these tests. Understanding this data helps engineers design cars that can perform at their best during races. Wind tunnel testing simulates real-world conditions by exposing a model of the NASCAR car to controlled airflow. This airflow is adjusted to mimic different speeds and angles. Engineers use sensors and instruments to capture important data on how the air interacts with the car's surfaces. Key measurements include downforce, drag, side force, and pressure distribution. Downforce is the force that pushes the car down onto the track, which helps improve tire grip. Drag is the resistance that slows the car down. Side force affects how stable the car is, especially when turning. Pressure distribution shows how air pressure varies across the car, indicating areas that may need design adjustments. Interpreting this data is all about finding the right balance. High downforce is great for cornering but can increase drag, which slows the car on straightaways. The ideal setup varies depending on the track and race strategy. To interpret wind tunnel data effectively, engineers follow several steps. First, they analyze airflow patterns. They might use visual aids like smoke or tufts on the model to see how air moves around the car. This helps identify areas of turbulence or separation that can be improved. Next, engineers compare aerodynamic forces. They look at how changes in components like spoilers or splitters affect downforce and drag. Evaluating yaw and roll angles is also important. Testing the car at different angles simulates real racing conditions and helps understand how the car behaves during turns. Another key aspect is iterative refinement. Each test provides data that informs adjustments to the car's design. These changes are retested to verify improvements. This process continues until the best aerodynamic balance is achieved. In NASCAR, wind tunnel data is often combined with computational fluid dynamics simulations. This digital testing allows teams to quickly evaluate multiple design options before building physical models. It speeds up the development process significantly. Practical applications of interpreting this data include designing effective spoilers and splitters that create downforce without adding too much drag. Engineers also shape body panels to smooth airflow and reduce turbulence. Adjusting aerodynamic balance is essential for stability and responsiveness in corners. Additionally, optimizing airflow for cooling systems is vital without sacrificing overall aerodynamic efficiency. Wind tunnels used in NASCAR testing may have rotating platforms to change the car's orientation quickly. They also maintain climate control to ensure consistent air density and temperature during tests. Ultimately, interpreting wind tunnel data translates raw measurements into actionable design changes. This process enhances a NASCAR car's performance on race day. It requires a solid understanding of aerodynamic principles and close collaboration between engineers and drivers. Together, they tailor the car's setup to meet specific track demands.